Whoops. Okay, uniform circular motion. I want you to try and imagine somebody. Imagine this is there's somebody, and this is the top of their head in the center of this diagram, and they've got a little aeroplane on a string, one of those model aeroplanes. Okay, um, and imagine they're swinging it around their head, or you can imagine a hammer thrower, and he's swinging the hammer around his head, and this circle here, or her head, this circle here is the path that the hammer itself, the ball or the aeroplane makes as it moves through the space around that person. Okay, what do you think those arrows represent? The direction of the velocity, yes, the direction and the magnitude of the velocity at those points, at each of these points here. Notice that the velocity is a tangent to the circle. If imagine me swinging something around my head. If I let that object go, what is it going to do? Yeah, it's going to go in a straight line at a tangent to that circular path, isn't it? So imagine this moment here. I let go at just that moment there. Of course, it doesn't fly out like a lot of people imagine it does. It doesn't go out that way at all. It goes in a tangent. Follows, yeah, that's not very good, is it? Follows this path if I were to let go at that moment there. Likewise, it would follow this path, same direction as the velocity was originally, if I were to let go at that moment there. Okay? So we can state something about that. We can say, I'm just going to shorten it to UCM rather than writing it all the time. An object in UCM, uniform circular motion, is moving with constant speed. Its speed is not changing. Its velocity is what? What am I going to say? Is changing. What do I mean by that? Direction, yeah, that's right. In that the direction is changing, is constantly changing. Um, what's causing that change in velocity? Louder? Yeah, okay, an acceleration. There's a resulting acceleration. There's an acceleration. Okay, we can start with that. There is an acceleration. In which direction? A. I'll put a little arrow above it to say that it's a vector. It has a direction, has magnitude and direction. Where is that acceleration toward? Yeah, towards the center. Towards the center of the circular path. So I'll draw that in now. Draw it in green, should be reasonably easy to see. Arbitrary length. Okay, there's our acceleration there. And at each point, I could choose any point here. It's always going to be pointing towards the center. And remember, we can say this by our acceleration is equal to the change in velocity per unit time. It looks like that's delta there. Change in velocity divided by the change in time. This acceleration is caused by what? By a force. Also toward the center. And what formula do we know that by? Force equals mass times acceleration. What are examples of this sort of situation? Well, a person with a hammer swinging around their head, an aeroplane swinging around. The control line airplanes. You guys got any experience with those? They were kind of old hat when I was a kid. So where somebody would have a remote control aeroplane and they had a control stick and two lines that went to the aeroplane, and they spun around with it, and you could control the aeroplane. It actually had a motor on it and everything. That was before radio control was really big. Okay, what else? What other examples are there of where we can set up uniform circular motion? Got any ideas? Satellites orbiting, yes. What's the force caused by there? Gravity, yeah, gravitation, isn't it? So with the aeroplane and with the hammer throw, there's a string or a cable, and we call that the tension force. We'll talk more about this in a second. Gravitation with satellites. What else is there? Atoms, atomic. So all right, let's draw some of these. So imagine person here with their. You have to excuse my overhead view of an aeroplane. Kind of looks like this. On a control line, or so model aeroplane. Person here with their arms out, and we could say the hammer throw. This is the Earth. We could draw a satellite orbiting. This is what I think satellites look like. They have antenna. Okay. There's no string here, is there? This one's gravitation. We could have, draw this in a different color. Here's a hydrogen nucleus with an electron moving around in some path here. If you guys have seen atomic orbitals, they're not really this shape. Atoms. What causes the what's that force that binds the nucleus to the electron, or the electron to the nucleus, whichever way you want to see it? It's what, say it louder. Electrostatic force. Electromagnetic, okay, yep. Electrostatic or magnetic. And what about this situation where we have this is a bend in a road and a car that kind of looks like an oval. There's a car moving around this bend. It's a bubble car. Yeah, I'm going to draw bubble cars. That's what my cars look like. So car on a bend. If that bend has no angle, what causes the centripetal force, or the acceleration towards the center of this circular arc here? Yeah, friction between the tires and the road, yes. You apply pressure on the steering wheel, that applies pressure to the front wheels, which applies pressure to the front tires, which applies pressure to the road pushes back and causes this turning motion. There can be other situation like when we looked at the Bugatti Veyron, where there's a banked corner, and I'll show you a video where they actually, you can go around these banked corners with your hands off the steering wheel. What provides the centripetal acceleration there? Yeah, the banking angle. Okay, we'll look at that in. So this here is called. Okay, so I'll put these in brackets. Electrostatic, car on a bend. Okay, we say friction here. And gravitation. So that's a satellite. And hammer throw model aeroplane. This is called tension force. Centripetal means center seeking. Force. Imagine if I have a projectile and this is a multi-image photograph of it. Taken at regular frequency. What could you say about that projectile at the moment? What are the things that you could say in physics? Has a constant velocity, okay, so constant velocity, how can you see that? Yeah, this distance is the same in each successive photograph, isn't it? So there's no change there. There's no change in velocity. Um, what could you say if all of a sudden it deviated from that path and instead of there, it kind of changed direction? What could you say about it on this path? Actually, I won't draw those in. That just confuses the issue. Changing velocity. What causes it? There's an acceleration due to some force. Due to some force. That force could be anything. You could imagine when we look at momentum and spacecraft, this ball could be quite complicated and have gas in it, and it fires gas out the side. Causing a force. Okay, so we have a velocity in this direction. We have some momentum of the gas in this direction, and therefore there's a force in that direction. So there's another situation where we'll get uniform circular motion. If that gas doesn't reduce in pressure and it continues all the way around, what's going to happen is this object will end up in uniform circular motion due to some force. Okay. So you can think of it like there's I used this last year, but think of it like if we look at our axes, Y and X, we've given where it had along this path here, it had no Y component of velocity. We've given it some Y component in here. All right. Let's see. We've already said about the example of the spaceship. We've kind of said that already. Oh, okay, we'll just go straight to one of our first formulae for this. A sub C means centripetal acceleration. A sub C equals, does anybody know what it equals? This says that the centripetal acceleration is directly proportional to the velocity squared and inversely proportional to the radius. An object somebody say centripetal. Centrifugal. Who said that one? Yeah, what's the difference? Does anybody know what the difference is between centripetal and centrifugal? Centrifugal is, yeah, it's I think it means, comes from center evading or something like that, going away from the center. what does that say? What if I increase V, then I increase the, if I double V, what do I do to the centripetal acceleration? Multiply it by 4, don't I? And the centripetal acceleration goes up by 4 times. If I double R, what do I do? Halve the centripetal acceleration. And that's, yeah, so imagine our person swinging something around their head. Everybody's done it at some point. They have something on a string, tethered to a string. Actually, no, I'll make that shorter. Tethered to the string, and they're swinging it around in uniform circular motion, some mass, m, and then they do the same thing, but with a longer string. How does it feel? Takes a while? What do you mean takes a while? Yeah, so the period of this motion is much larger, yes. Okay, this is moving. You could imagine to swing this around your head just to keep it up above around your head, you have to move that quite fast. This one you don't have to move so fast, do you? Some people will have some experience with this. Makes it intuitive. Double the radius, you reduce that acceleration. Okay. We're going to go to a video now. Oh, yes. Is that the one I want to go to? Yes, I think it is. It's called derivation of formulae. Say that again. Oh, okay. Yes, good idea. Off you go. How much time have we got? 20 minutes? Half hour? Thank you. This is exciting video, but not just now. Oh, we've been recording all this time. Let me see. I'll get a circle. This person said, okay, so we have a velocity v here, and then a moment later, delta t later, we have another velocity. Shh, please. And you could say this is v1, this is v2. Okay, that's not so hard to understand. How do I add these vectors? V1 plus minus V2. Okay, because what is change in velocity? The change in velocity is V2 minus V1 or V1 minus V2. And so when we do that, have a look at this. Here's V1. I'll try and draw it similar to how it is on the diagram, but a little bit bigger. What does minus V2 look like? Yeah, upside down, so in the reverse direction, it should be a straight line. Looks something like that. So this is V1. This is minus V2. This here is what? Yeah, your delta V. Okay, from the video. So, and this, what they're saying is that this is approximately towards the center of the circle. If this time interval is small enough, or the smaller that time interval between V1 and V2, the closer towards the center of the circle it's going to be. The other final thing that they said, the final thing that we'll say today is that from Newton's second law, F equals ma, and we know that A in this case is centripetal acceleration is equal to V squared over R. We can say from that that the centripetal force F sub C is equal to m times V squared over R.